first thing that I want to do is hand out something related to senior orals. So I'm going to try and.
I'm proud of myself though, I have started.
Well, that's good.
Started making this.
It won't let me launch the meeting from my laptop.
Okay, well, you're fine to view it via the phone. It's just going to be kind of small, but I'll record it so that if you can't read things, you can go back to the recording and see them. Will that work?
Yeah, I can try.
All right.
That's
That's not it. There we go. Okay. And two. Share this. And when you two get back, I'll get you a copy of this as well. I wrote this up a couple of years ago as just kind of a way of giving you guys an idea of what to expect. So the top part just kind of talks about the kinds of questions that you'll have, and that will depend on whether you're a chemistry major or a biochem major. Note that biochem will also answer a biology question, so be prepared for that. You won't be asked questions from courses that you haven't taken. So if you didn't take analytical, you're not going to have an analytical question, that kind of thing. Let's see, expectations about what you're doing. You should definitely go over significant figures and stoichiometry. You should be able to take a formula like PV equal nRT and solve it for one of the variables. So that's what I mean by manipulate a formula. Particularly if you've had classes with Dr. Fraley, he will often ask about how does this particular kind of equipment work. So make sure that you go over that. And then we like to see that you know some of the basic chemical formulas and which ions are positive and those kinds of things. All right, Ashley's got our computer working. So we typically will expect people to pass. Generally, if people are not passing, they're showing a pretty big weakness in one of those areas. We don't make you redo the entire test, just the area that you showed that weakness in. And so we may set it up as a mini oral exam that you would do later in the semester, or we may just set it up that you have to meet personally with a professor that covers that. So that's how those things work. You are expected to dress professionally for this. So it's kind of as if you were giving an interview for a job, or if you were, doing your senior oral, not exam, but the presentation for seminar. So supposed to be dressed nicely for those kinds of things. So this is just something that can kind of help you get a sense of what it is you're looking towards. And as I said, for Ashley and Harper, I'll have a copy of that when you guys get back.
I like how it says, understand the stress of the day and make all the mental slips.
When I was in grad school, you had to take what were called cumulative exams. And so each exam was worth 1 point. And you had to accumulate 5 points, and you could either get a 1, a 0, or a half. And so you had to do it until you got 5 points. And then you had to do an oral, much like the orals that we have you do, before they would officially admit you into the PhD program. And when they did that for my oral exam, they asked me about the group 6 elements. And I started thinking about oxygen and sulfur and selenium because I was thinking of the old style of numbering. And they're like, but we mean like chromium and that column. And so they asked me what the other elements in that column were. I didn't have a periodic table. And like, I couldn't even get beyond what the question was to think about what the answer might be. I just froze, but I ended up passing, so. Yes, we do understand mental slips. Yeah, this, you'll be in here and have this, or you'll be in one of the rooms across the hall that have them. We're not going to take them down. You'll have periodic tables. Yeah. Okay. So a couple of things that I wanted to go over since we're doing a quiz. And actually, just for reference, where did we stop on Friday? Resonance. Okay. And did we just talk about equivalent resonance, or did we talk about non-equivalent resonance as well?
One non-equivalent.
Yeah.
Like, we stopped it.
Okay.
We did
Okay.
CO2. There was an example of CO2.
Okay. All right. So, first thing I want to go over is dipoles. So hopefully you all remember that if something is a dipole, it is a polar particle. Usually we think of that as a polar molecule like water. But in theory, it could just be any random object that was polar. And the important thing about this is that I put on this on your quiz, and then I wasn't sure if we had gone over this. We indicate polarity by the dipole arrow. That look familiar to you? You've seen that in other classes? So arrows in chemistry generally are showing you electrons. So this side is the partially negative side. The arrowhead is the partially negative side. And then the cross side, fortunately, looks like a plus. That's the partially positive side. So if something is polar, what do we say it has that we can measure? How do we measure how polar something is? How do we measure that?
Difference in electrical activity between the bonds.
Call it a dipole moment. So sometimes we'll show a difference in dipole moments by having the arrow be longer or shorter. We're not going to do any calculations with this, but we should have the general sense that if elements are farther apart on the periodic table, probably that's a more polar bond. If they're right next to each other, that's going to be a less polar bond. And then if they're the same element, it should be a non-polar bond. So I would expect the boron-carbon bond to be polar, but not very polar. But I would expect the boron-fluorine bond to be very polar. All right. So anything about that seem confusing? Yeah.
Are we gonna, what is that formula for the dipole? It's like mu x is equal to,
I don't know.
you know.
I'm not gonna use it.
Okay.
Yeah, because molecules are three-dimensional. And so by the time you start looking in 3 dimensions, it just becomes really complicated and you have to plug it into a computer anyway. So I don't find it useful to try and solve that. So no, you don't have to calculate it, but I do want you to be able to look at something like I've given a boron carbon bond and tell me, well, which direction would this arrow point? To carbon, because it's closer to fluorine and it's more electronegative. All right. Okay, let's keep an eye on the time. I don't want to talk too long. All right. So we have been talking about resonance. And this is where we can move the electrons around. And so one thing to remember is that we can have bonds that are sort of in between single and double bonds. So if I'm looking at something like nitrite, was this the example I used?
They use ozone as the example.
Okay, well, this one. So if I'm looking at nitrite,
Nitrate.
nitrate, thank you. If I'm looking at nitrate, it looks like I have 2 single bonds and 1 double bond, but in reality, I'm gonna find that my bond order for each bond is in between. And I can calculate that by counting the number of these lines. Which I'm gonna call the total bond order. I'm not going to call it the number of bonds because technically a double bond is just 1 bond. So the total bond order is 1, 2, 3, 4, and divide that by total bonds. So I have a bond order of 4 divided by 3 bonds, a single, and a double. And so each of these bonds acts like it is a 1 1/3 bond. So it is a little bit stronger than a single bond. What happens to the length as you go from single to double? Does it get shorter, longer, stay the same?
Shorter.
Shorter, very good. Yeah, so. And then the trend continues on to triple. I'm not going to write triple, but this one is long. Double is short. Triple is shortest. And then this one is going to be weakest. And this one's going to be stronger. And then strong does not have any on it. Triple would be the strongest. And so this 4 1/3 is going to kind of fall in between the 2, but closer to a single bond. I'm going to have to put more energy into breaking the nitrogen oxygen bond than I would for a typical nitrogen oxygen single bond. But I'm not going to need to put in as much energy as I would for a nitrogen oxygen double bond. All right, so when we are doing dot structures, it's important to remember that our second row, where most of the elements in organic chemistry are, hydrogen is first row, but carbon, nitrogen, oxygen, fluorine, those have to follow the octet rule. The third row and anything greater than the third row can have hypervalency or an expanded octet. So I usually call it an expanded octet, but some books say hypervalency. So we can see this in a couple of ways. One way is sometimes we'll have more than 4 atoms attached. So if I have more than 4 atoms, then I have more than 4 pairs of electrons in a bond, and I have to have more than 8 electrons. So PF5, if the phosphorus is attached to 5 fluorines, there's no way to do that without it having at least 10 electrons. So that one's kind of obvious, but then we can also have examples where we might have only 4 bonds or fewer than 4 bonds, but we still have hypervalency. So one example would be SF4. This one's less obvious. So we have 6 electrons for sulfur, 7 for fluorine, 4 fluorine atoms, so that's 28, 34 electrons. So I might try and draw it like this, but if I count these up, this is 8, 16, 24, 32 electrons. So I need to have 2 more on the sulfur. So if I have extra electrons and no place to put them, then sulfur, which can be hypervalent, will take on those extra electrons. So sometimes we'll see lone pairs in addition to the typical bonds. The other thing we can see is non-equivalent resonance, in which the double single bonding can change around on a molecule. So if we look at SO4 2-, we didn't look at this yet, did we? Okay. We might typically draw this like so. So it only has 32 electrons. We would, of course, put our charge out there. But it's actually more stable like this. So it's got some hypervalency there. So then the question becomes, how can we tell which is going to be the more stable form? And the way that we do that is with formal charge. And for every atom, we can calculate valence electrons minus lone pair electrons minus half the bonding electrons. And that's the same thing as the line. All of the lines are half the bonding electrons. So we can calculate this for each atom, but what do we do with it? We want to have a formal charge of 0. So ideally, every element is 0. And so you probably learned over the years, carbon always has 4 bonds, oxygen almost always has 2 bonds. It might be a double bond, or it might be 2 single bonds, but it always has 2 bonds. This is when we have that formal charge of 0. And we know that we can have some variations. Sometimes we see nitrogen with 4 instead of 3. Sometimes we see oxygen with 1 instead of 2. But usually we see that one scenario. When we are hitting those ideal number of atoms, we get that formal charge of 0. Let's take a look at the sulfur here. Actually, let's look at the oxygen first. So the oxygen that is singly bonded, we take 6 valence electrons minus 2, 4, 6 lone pair electrons minus 1 bond, or half of the pair of bonding electrons. And that gives me a -1 formal charge. So I can indicate that in a little circle next to each of these. This is going to be true regardless of the molecule, because it doesn't matter what it's bonded to, it only matters what its bond order is. If I'm looking at, yeah, I'm still on this. The sulfur in this first one here, I'm going to do 4 lines coming out. It's also in group 6. Lone pair electrons?
0.
0. And bonds? 4. So we end up with a +2. So that's not 0, and it's not even close to 0. It's not like it's a 1 or anything. So this is not a good scenario. But let's tilt this just a little bit so I don't have to start a new line. If I look at the sulfur where I had 2 double bonds, I still have 6 valence. I still have 0 lone pair electrons. But my bonding electrons that count towards the sulfur, there are 6 lines that I've drawn, and I get 0. So we're always better off if we can get all of the atoms close to 0. But if we have a charge, we can't get everything close to 0. So if there's a charge, the more negative goes on the more electronegative atom. So if I have an arrangement that has sulfur is -1 and oxygen is 0, and I have a different arrangement that has oxygen is -1 and sulfur is 0, I'm going to pick the one with oxygen is -1 because that's the one that, because oxygen is more electronegative. All right. Does this sound familiar from Gen Chem? All right, questions about formal charge? Okay, so we are going to be getting into some of the newer material in chapter 3. So you should be reading, I think it kind of intermingles some of the new stuff with VSEPR theory. So review VSEPR shapes. We won't spend a lot of time on that, but be reading section 3.2.